So thank you. I'm sorry. I'm a fill-in moderator. The original moderator couldn't be here. One of the co-directors of the program. So this session is, we have many projects, and we just invited a few of the participants to sort of talk about some of the example projects going on here. And the first, we're going to start with Christina, who's, as you just heard, is a professor, but going to talk about the work on human and physical limitations. So, Christine, it's up to you.
Okay. I should go there? Okay.
Sure. Why don't you stand up?
Okay. Okay. Thank you. So, hello, everybody. Thank you very much for the invitation, for being here. It is a pleasure to be able to share our research with this community, and I will present the work we have been developing under this MIT funding project, which is Pain and Physical Limitations Perception for Human-Sensitive, Intelligent, Collaborative Robots. So, I'm sorry, okay. So, first I will present academia, and this is a joint project which involves University of Minho with this team you can see there, and it also involves MIT, in which we have Professor Mercedes and Professor Elazar. And then we have this PhD student, Sara Cerqueira, which is currently visiting MIT under this project. Then, because we always try to develop our solutions following a user-centered approach, we also involve the end users, namely, we involved ergonomists, and we also involved roboticists from Bosch, Braga, Eurico is from Braga, and then Ana Pombeiro is currently at Germany. And we also involved a physiotherapist from a local company, Terapias Partilhadas. So this provides a multidisciplinary team that will be able to provide and do a final solution that is able to focus on usability and thus acceptability. And thus, it appears our motivation. Our motivation is work-related musculoskeletal disorders. And in order to explain to you our motivation, I thought of this persona case, which tries to embody one possible situation. So let's consider Maria. This is Miss Maria. She's 52 years old and has been working on a production line for 15 years. And over the years, due to her profession, she developed a shoulder lesion. And she took a 6-month sick leave and did rehabilitation. Of course, after the leave, she returned to work, but the fact is that the injury has made it harder ever since. And with time, what happened is that Maria's motivation and sense of purpose became affected. And the fact is that this motivation is there because industry has a high physical demand on the woman worker. And this can result in work-related musculoskeletal disorders. And I spoke about Maria, but the fact is that Maria represents 60% of the European workers that suffer from a painful musculoskeletal disorder. And also, 30% of these workers with musculoskeletal disorders will not be able to work until the age of 60. Furthermore, 30% of the years lived with disability are due to these work-related musculoskeletal disorders. So, this is in fact a concern, and it is a mondial concern nowadays that people are talking and aiming for healthy aging. In fact, if we think in 2020, the number of people aged 60 years and older outnumbers children younger than 5 years. Furthermore, between 2015 and 2050, the proportion of the world's population over 60 years will double from 12% to 22%. Also, this will have consequences. This will lead to higher injury risk and shortage of workers. And we have to consider several impacts this can have. This can have productivity loss, which will have an economic impact. And this economic impact has also to be considered not only the societal impact for which the one I started, but also the economical impact. And this was our concern, these two problems, and for that we tackle this idea of healthy aging and musculoskeletal work disorders. So what is the need? The need is for work-related musculoskeletal disorders, preventive workstations, and also to develop more inclusive workstations. And we tackled these two problems, and we leveraged on the fact that collaborative robots are already available at many workspaces. So we should take advantage of this and propose for digital solutions. So our goal was developed in two big goals. Our first goal was to develop a woman-sensitive controller able to identify and assist workers with physical limitations by minimizing their pain-inflicting movements. And a second goal, which was to improve women ergonomics and performance in the workplace. This is aligned with Sustainable Development Goals. It is aligned with the third of good health and well-being by enabling detection of pain and promoting understanding of workers suffering from this pain, and also reducing these work-related musculoskeletal disorders. It's aligned with the eighth goal of decent work and economic growth, and to promote productivity towards sustainable health and employment, and promote workers' inclusion while keeping their well-being. And finally, is also aligned with the ninth goal of innovation and industry and infrastructure by enabling new ergonomic assessment values and advanced technology, robotics technology for a safer work. So, what is the vision of integrator? What we decided, and here in red you can see the integrator contribution. We took a worker which will be instrumented to collect the data, namely kinematics, muscle activation, and heart rate. This will be collected, this data of uniarticular movements and industrial task-oriented movements, and we published a public data set following an open science approach in which we expect to give data to others so more algorithms can be developed. This data is then used in a block of assessment. This assessment will do an ergonomic assessment, a productivity assessment, and an innovative pain biomarker assessment. This assessment is able to, I was trying to figure out where. Okay. This assessment will calculate pain level, ergonomics, and productivity scores, which will feed our block of physical limitation ergonomic risk management, in which integrator will develop an ergonomics and physical limitation sensitive controller. This controller basically will decide the movements of the cobot such that the resultant movement aims for a well-being of the worker and reducing their pain. So, following this vision, we started first by data collection. We aimed for two groups. A first group with health participants with delayed onset muscle soreness, and a second group with participants with shoulder pain. We have already collected this first group of LC participants with soreness, and for that, we collected 17 participants following an ethical commission we have approved in University of Minho. And as you can see here, we have our volunteers working until being fatigued, so that they would be with pain in their muscles. And we went for that for several hours to a gymnasium. And then we did our data collection, in which the 7 participants performed some industry-related movements and tasks that they would have to do, which would then we could assess their pain. So this was our first collection. The second one is currently undergoing, and for that we are still recruiting and collecting data. This will be done with our partner physiotherapist in Terapias Partilhadas, so that he can, following this multidisciplinary approach, provide for guidelines including physiotherapy. So this is the first block. The second block, we are developed the pain biomarker, in which we will took this data that we collected, and we will apply deep learning algorithms following artificial intelligence approach that will provide for a pain level assessment. This is currently being doing also in MIT with Sarah, that is currently there, in which we will use the knowledge of Dr. Elazar and Mercedes about heart rate. So these scores will then, the sensing and the perception will then feed our last block. It's not moving, okay. Will then feed our last block of risk management, which will provide for the control of the robot. For that, we are using state-of-the-art approaches, following reinforcement learning in particular, which will be used to adjust the position of the robot accordingly, such that the final movement does not provoke pain. For that, I brought a movie in which you can see a collaborative task. The aim is to take the board until, I hope this doesn't fall, so up here. And this will be a painful situation for the person, and our controlling is calculating the best movement the robot and assistance the robot should provide to minimize the pain that the person is suffering. Okay, and that we have already these achievements, some publications with scientific impact is also very important for the academia and for dissemination. And that is my presentation. I hope you enjoyed it. Thank you.
Thank you, Christina. I think we have a minute or two if there's any questions from the audience. Okay, we can take it on afterwards.
Okay.
Right, thank you. The next briefing will be by Dara Enkanabi, along with his collaborator, Isabella Drago. This is related to our focus on climate change, and we'll be talking about abrupt changes in regions at the climate tipping point.
Well, good morning, and thank you for the opportunity to tell you a bit about our project that is a collaboration with Isabel Trigo, who's here, and my group at MIT. And we've been looking at climate change, indicators of climate change, and specifically with using satellite data to look at the impacts of climate change. And I'll go through it step by step. This is a figure that's been used in IPCC, and it's become quite a popular depiction of what are called climate tipping points. So these are impacts of climate change that go beyond the steady warming of the atmosphere due to change in the composition of the atmosphere. So these are events that happen abruptly, that's the key word, and they have long-term impacts or large-scale impacts. Key among them is the, for instance, well, just around, it doesn't show, okay. Key among them is in the middle, the weakening of the AMOC. That's the Atlantic Meridional Oceanic circulation. That's a slow circulation of sinking cold waters in the high latitudes. It goes deep in the ocean and comes to the rest of the Atlantic basin and even beyond. That circulation can abruptly stop and would have devastating climate consequences, weather consequences. So that's an ocean circulation one. At the very top and the very bottom are loss of land ice sheets or land ice. When we talk about land ice that's not part of the ocean now. So when it melts, it adds to the ocean. Or the sea ice would be, in a sense, a neutral component. But with the melting of the land ice, that water is added to the oceans. The oceans are thermally expanding anyways. So that would be an abrupt sea level rise. And the last one in the middle is the dieback of the Amazon forests. The Amazon forest is susceptible to sudden diebacks and complete change of the vegetation cover, so that's abrupt. What's notable about all four of these as tipping points is that they're irreversible, at least in our lifetimes. When you melt ice over land, when you stop the meridional circulation, when you disrupt a forest, it takes generations for it to come back. So that's what makes them tipping points, and that's why searching for tipping points in the climate system is a priority. So that's sort of where Isabel and I have been working on, but looking for other tipping points. The tipping point we're looking for is over land, where we live and we inhabit. And over land, there's the water cycle, the energy cycle, and the carbon cycle. These three cycles are the three main metabolic cycles of the Earth system, and over land, they're very much linked. The link is important because they're like gears in a clock. If you perturb one, that perturbation propagates to the other cycles. So it's not just perturbing that one cycle. The key question is, how does it propagate from one cycle to another? You may just disturb the energy cycle, but it has a consequence due to that coupling. So these three main metabolic cycles of the climate system, especially over land, are gears that turn together. How they are linked, the size of the gears, the size of the cogs, and so forth, are sort of closure relationships in models. And it links all three of them. And each model has its own way of making that closure, making that coupling, which leads to uncertainty among models. That's why there's so much model spread in projections of the future. And let me just, as the title of the slide says, what is the statement of the problem? What is the problem we have? These are just 6 out of maybe a dozen or 2 dozen climate models that are out there. Doesn't matter which one they are, the names give them away. The first one's Canadian, and so forth. Doesn't matter. 6 models that we use for climate assessment. And this is how, these are model output, over a piece of territory like you see in yellow, they couple the water, energy, and carbon cycles. EF is evaporation, normalized to be between 0 and 1, so it's evaporative fraction. That's part of the energy cycle. On the x-axis is soil moisture, which is state of the water cycle. And on the y-axis, in the second graph, is the gross primary productivity. That's the carbon cycle, grams of carbon per meter square per day. That's the flux of carbon. And what you see that among the models, there's very little agreement about what that closure should be. And hence the uncertainty among models. Basically, this is the problem that we need to solve. So, Isabel and I both work on observations of the Earth system using satellites. So we need, in order to get an independent observation-based estimates of these, you need to have independent observations of the X and the Y axis on all graphs. So we have soil moisture data from the project I work on that's in operation right now. We have weather stations, and we have observations of the carbon cycle using solar-induced fluorescence, which is a really neat new measurement. What it is that during photosynthesis, you take carbon dioxide from the atmosphere, water from the soil, and energy in the photosynthetic active radiation band. During that chemical process, some of the energy is fluoresced. It means that the energy that's absorbed is released in a different frequency, and that's over and above what the sun gives. So measuring that gives you an estimate of photosynthesis directly. So this is the same graph now, but with purely observations. On the x-axis and the y-axis, same graphs, but with observations. And what the top shows is the coupling between the water and energy cycle, and the bottom shows is the coupling between the water and the carbon cycles. This is the benchmark the models must meet, because this is purely observational. Now, what you see in the top graph is that there seems to be a two-regime behavior. The water and the energy cycles are linked, but with a transition point distinguishing two entirely different regimes. In one regime, the soil moisture the water cycle is severely limiting the energy cycle. They're very strongly coupled. And to the right-hand side, there's a regime where they're decoupled. So how often you're in these regimes is a nonlinear response, because you're changing regimes. You're going across a threshold. In the carbon cycle, you see the same two-threshold behavior, but with different plateaus. Different levels of carbon flux, because you got different types of vegetation that have different capacities. So that aside, let me go one step further and look at what happens during, not just on average, but during an event. This is a conceptual graph. When you have a storm, you moisten the surface so the water cycle becomes engaged, and then it dries over time. That's the blue line. So soil moisture is decreasing over time. The green line is the evaporation, is the energy cycle response, and it has that two-regime behavior. At the beginning, it's energy limited. There's plenty of water, not enough energy to evaporate, change the phase of water. And then at a certain threshold, the regime changes. There's plenty of energy, but not enough water. So then the water starts influencing the energy cycle. The signature of that you can see with the satellite is the red line. When you limit the amount of evaporation that can take place and, in a sense, take up heat, then the surface temperature goes up. So we should see that in the anomalies of surface temperature. Now, this is sort of the collaboration between Isabel and myself, is that Isabel has been working for many years on the Meteosat series of satellites that are geostationary satellites, and they measure temperature and visible and infrared measurements. And I work on the soil moisture active passive, which is a microwave mission in low Earth orbit, and it measures in very low frequency microwaves, very close to the cell phone range. These two satellites are about as as far as Earth observations go, as different as can be. One of them is visible infrared, geostationary orbit, every 15 minutes of data refresh rate. This one's microwave, invisible to the eye. It's in low Earth orbit, and every 2 days. But it turns out that in our collaboration, there's incredible synergy. There's incredible science questions you can ask by combining these two. So we're looking at those regions in different colors, and this is the conceptual graph, but now with data. As the soil moisture dries, goes from high 0.6 to 0.1 or so, the temperature response from morning to afternoon is unaffected during the energy limited regime, and then you hit a threshold and you change regimes, and then it shoots up. So you see the conceptual graph in real data. And also, it has other impacts. Remember this, I'll come back to it. If you look at the boundary layer, the amount of humidity in the boundary layer, the vapor pressure deficit also follows the same trend, as we'll see what it means later. So between the two satellites, we estimate the thresholds at which you change regimes. So these are soil moisture thresholds at which you go from one regime to another. You cross a threshold, and therefore you cross a nonlinearity. You create a nonlinearity. It depends on climate, but also, surprisingly, it depends on the soil texture. What is the hydraulics? What is the capillary forces holding back water? Actually, it turns out matters for these thresholds. So here's a question Isabel and I first posed, was that the question at the top. Again, we're looking for tipping points, surprising tipping points that we didn't know existed, but we're going to stumble across it in the dark. So the question we asked, are regions with the largest climate variability necessarily the ones with the largest land surface response? Meaning, is that regions of the world where the land local microclimate is going to see the most change, are they necessarily the ones that are being kicked the hardest by the climate, by precipitation? If not, that's the telltale sign of a tipping point, because it's not linear response to a forcing, but a surprising nonlinearity. So, as the bottom says, the discovery of those tipping points is the discovery of the regions which are most vulnerable to climate change. So, as I mentioned, there's different regimes, and this is, for instance, the fraction of time you exist in based upon observations in one of those regimes. Now, if the threshold is that vertical line there, energy limited, water limited, and the response, like you saw, is the red line, the probability distribution function, where you are climate-wise, matters. If you are purely in one energy limited regime, you're less vulnerable because you're not changing regimes. If you're in the other one, you're changing regimes. If you're at the boundary, you're changing regimes. So the probability where you are climate-wise relative to this nonlinear threshold is a tipping point. So the summary of the response to the question is that if you look at how much we kick the system, precipitation into annual variability versus this energy balance surface response, microclimate response, of course, is increasing, but the slope of the increase, the sensitivity, depends on the amount of time you spend in one regime or another, meaning how close you are to that regime change. And with that, this is the final figure, we have a metric between 0 and 1 of land tipping points. Where in the world the variability of the microclimate, temperature, humidity, is not necessarily explained by interannual variability of forcing precipitation, but by subtle changes that cross these thresholds. And we see a few hotspots that are noteworthy. For instance, in the US Midwest, in the Pampas in Argentina and South America, in Eastern Europe, across the Indian subcontinent, and Eastern Australia. Those regions should be familiar because those are the bread baskets of the world. Those are where rain-fed agriculture is feeding the world. And it kind of makes sense in retrospect that the most vulnerable regions and the bread baskets must coincide. Where would you put a bread basket region? You would put it where it's not so dry that you would need irrigation all the time, and not so wet where the soil is leaching so much that it's poor quality, it's low in nutrients. You put it at where those transition points are, or they develop where those transition points are. And it turns out they're the most vulnerable to climate change. So bibliography of the work that Isabella and I have done and collaborated in the last few years is listed here. And in summary, this has been a long-standing collaboration between Portugal and MIT colleagues going on 5 years now in topics of mutual interest in climate change. The key enabler was that each of us, Isabel and I, are leads in 2 satellite projects that are about as different as can be as far as Earth observing satellites go, but there's incredible synergy between the 2, and we've used that to our advantage. And so basically, I think what we've been trying to do is to create observation-based benchmarks in how Earth system models must behave. That's the statement of the problem I had at the very beginning. And how they couple the water, energy, and carbon cycles, and find, besides the Atlantic circulation, the ice sheet melts, Amazon dieback, discover other tipping points that define regions that are particularly sensitive to climate change. This is the last slide, where we're going next, is look at this in a system dynamical framework. So we're looking at the stability of the system by fitting it to a system dynamics framework, and look at the the stability of the system. So that's what I had. Thank you.
Thank you, Dara. Maybe one question if we're, yeah. Okay, we got to. While the question's coming on, notice, by the way, this is beautiful work. Portugal is a hotspot on your thing. So are there implications directly for what you should be looking at in Portugal from the vulnerability standpoint?
Yeah, this is also
Mike.
transitional. This is the Iberian Peninsula is a transitional climate, and it's vulnerable to major climate changes. For instance, the Valencia floods that we recently had, it came on top of earlier events that basically put the system in a state that made it particularly vulnerable. I mean, getting 20 inches of rain in 8 hours is bad enough. But if you look at the soil moisture maps before that event, it was a long-standing event. So basically be on the lookout for
the... Okay, question.
Thank you. Antonio Graça, Head of Research from Sograppa Wine Company. I wonder what was the spatial resolution that you could get in your analysis, and how far down in downscaling can you go using this approach?
Yeah, Another major contrast between the two satellite systems is that the satellite system Isabel works on has kilometer, sub-kilometer resolution. The one I work on has 30-kilometer resolution. It doesn't resolve field scale phenomena, but it resolves climate scale phenomena. So there's definitely, it reaches some application, it doesn't do other applications. There's plenty for us to do with what we have. There's plenty of work.
Okay, thank you, Dara. Okay, the next in the final briefing for this session will be by Alicia Saccone, and she's actually going to be talking about toxicity effects of wildfires, which is another impact of the climate change. And she's a graduate student filling in for her advisor, Noelle Salone.
Hi, everyone. My name is Lexia Sassoni, and as mentioned, unfortunately, my advisor, Noelle Salone, wasn't able to make it, so I'll be presenting on both some of my research as well as one of my colleagues, Eric Roy's research under Noelle's supervision. So I'll be talking about global and regional wildfire emissions of toxic pollutants and how those contribute to health risk. So starting broad, the impacts from wildfires are being felt all over the world. And I think a lot of us can start to attest to that from personal experience. And so in summer of 2023, for those of you that were in the MIT area, we were actually able to see the impacts from Canada's wildfire on New York and other kind of northeastern region in the US. And we could see that actual smoke haze. Within Portugal, we see that there was actually recent wildfires that happened just this past September that were really devastating. We saw in Australia really severe wildfires taking place in 2020 that actually were able to loft up into the stratosphere, and those all having really severe effects on air quality. And so overall, we're seeing this trend where the reach of wildfire smoke is going global. And so there was a study back in 2021 that was able to look at air quality on a global scale. And so they found that over 143 countries were actually experiencing air quality that was exceeding the World Health Organization guidelines. And so this was assessed based on particulate matter, so PM2.5, which is particulate matter less than 2.5 microns. And this is often used to assess health effects of both wildfires and air pollution in general. Globally, 44 million people are exposed to unhealthy air. And looking specifically at the impacts of wildfires, landscape fires that emitted PM2.5 actually resulted in over 600,000 premature deaths. And so I wanted to emphasize that there's actually a really important human impact on these wildfires. And so this was a paper that came out of our group last year. And so it showed that agriculture and human-initiated wildfires actually dominate fire PM2.5 smoke within the US. And so the smoke from these fires actually contributes between 5 to 10% of overall PM2.5 levels within the US. And this accounted for more than 80% of the population-weighted exposure and premature deaths associated with fire PM2.5. And then there's, of course, the other obvious human lever, which is climate change. And so here was just one study that pointed out that the likelihood of catastrophic wildfire events will increase by a factor of between 1.3 to 1.57, even under the lowest emission scenarios. And so, of course, this is going to vary by different regions, but overall we're seeing an increasing impact from wildfires, even as we try to mitigate the anthropogenic side of air quality. And so, as I mentioned, wildfire health impacts are often assessed based on PM mass. And so here I'm showing an example of some of the molecules that are emitted when you have a wildfire. So again, you can see the particulate matter, but you also get other emissions such as CO2, methane, and the focus of this talk, which is mercury, so Hg, and PAHs, or polycyclic aromatic hydrocarbons. And so I emphasize these because these both exist in the gas phase and the particulate phase. And so it's been known for a while that concentrations of particulate matter are not only higher during wildfires, but they're actually a lot more toxic. And so there's really this need to consider toxic air pollutants when looking at wildfire impacts. So just a little background on mercury and PAHs. So mercury, elemental mercury in the atmosphere is able to be taken up by vegetation. And so when you have a wildfire, you are re-emitting that mercury into the atmosphere. This mercury undergoes oxidation and reduction chemistry and can ultimately deposit either onto land or into water. And so in the water, you can get, again, this kind of redox cycling, but you also can get the formation of methyl mercury. And so this is the really important species for health impacts because the methyl mercury can bioaccumulate within fish, and then when people consume this fish, it can have really severe health impacts, such as issues with your kidneys or other neurological issues. Looking at PAHs, again, you get emission from PAHs from wildfires. This takes place from the incomplete combustion that takes place during wildfires. And again, you get this kind of partitioning between the gas and particle phase and oxidation to form degradation products. And those degradation products have actually been shown to be maybe even more toxic than the parent PAHs. And so when these PAHs are breathed in, they're actually carcinogenic and so have really detrimental health effects. And so our research with that background kind of looked at two different questions. So one, what are the wildfire impacts of toxics on health globally? And two, how effectively do global models capture regional pollution events? And so we use the 2017 Portugal wildfires as our sort of case study in order to address that second question. And so here I'm showing satellite imagery where you can kind of actually visualize the smoke that resulted from those wildfires. And here I'm showing the burned area resulting from different wildfires across the north, center, and southern region of Portugal. And so you can see that that 2017 wildfire was a really severe wildfire. And unfortunately, I don't have the updated data on this year's wildfires, but I assume that those would also be pretty significant as well. And so how do we answer these questions? We use a global chemical transport model in order to represent mercury and PAHs in the atmosphere. And so we specifically use geochem. So this intakes things like emissions, your meteorology, land cover. It solves this continuity equation, looking at both chemistry, deposition, emissions, and basically outputs some sort of diagnostic like your concentration of air pollutants. And it does this by kind of breaking up the globe into these different grid boxes. And so to answer our questions, we did 3 different model runs in order to isolate the impacts of both global fires and the 2017 Portugal fires. And so we did a kind of standard run with our typical emissions inputs. We then ran a no biomass burning scenario, and then finally ran a no Iberian Peninsula biomass burning scenario. And so by looking at the difference between the standard and these other 2 scenarios, we're able to isolate the effects of those wildfires. So how well does our model do is a big question. So starting with the mercury results. So here you can see in those sort of diamond shapes are our observations that are available, and the background color is our model. And so you can see that it does a pretty good job of resolving different spatial patterns. Here I'm plotting the observed versus modeled concentrations. And so you can see that, of course, our model tends to underestimate mercury concentrations. That's pretty typical of a global model of this resolution. But in general, what we're actually seeing is that, if anything, the results that we're finding are actually even more significant for concentrations and health effects. So we see similar trends for our PAHs. So here I'm just showing 3 different PAHs for comparison. But again, you can see that it does a pretty good job at resolving the different spatial resolution patterns. As you can note, PHs have a very severe lack of observations, so we really only have them for North America and Europe, unfortunately. But again, we're seeing when plotting that observed versus modeled concentration, we're seeing a kind of underestimation, likely due to our model resolution. So some results. First, looking at the global picture. So here we're looking at annual mercury deposition, and this is the % contribution from wildfires. And so here you can see large deposition contributions in typical biomass burning regions like Africa and the boreal regions. When looking at PAHs, again, we see a similar trend. Here I'm plotting the % contribution of wildfires to pH concentrations globally. And we can see that pH concentrations actually cover a broader range of active fire regions, but again, we see those kind of similar hotspots in areas where we expect wildfires. And with PAHs, we can actually take this a step further, and we're able to actually calculate the contribution of wildfires to cancer cases. And so here you can see that the cancer risk is really focused around areas with both high population and that are very wildfire prone. So let's zoom into regional impacts. So again, plotting the % contribution of wildfires to mercury deposition, and you can see that the deposition is really focused right around the emission region. However, when expanding that to PAHs, you can see that the PAH plume actually really extends northward and has a kind of more broader reaching impact. And so when we break that down into cancer cases, you can see there's, of course, contribution right where the wildfires are taking place in Portugal. But you can also see a secondary peak taking place in Western Ireland. And so these regional impacts actually are able to expand more broadly. And so, as you might have noticed, Portugal really is only a few grid boxes in our model, and so we really want to address the question, how does model resolution impact both mercury and pH concentrations, as well as their health effects? And so that's where our collaboration comes in with a group from University of Aveiro. And so our ultimate goal with this project is to work with our collaborators to leverage high-resolution regional air quality models. And so here I am showing results from the model that they actually have and use consistently in their research. So here we're showing PM10 air concentrations, again from those October 2017 Portugal wildfires. And so here they're actually using the Whorf-Khmer model. And so they actually, whereas our models get at a like 2 by 2.5 degree resolution, they're able to get it down to a 5 kilometer by 5 kilometer horizontal resolution. And so our ultimate goal is to kind of join their regional modeling abilities with our ability to model air toxics like mercury and PAHs. And so to conclude, overall, we see that wildfire emissions contribute a large fraction of the annual mercury deposition and pH exposure, contributing about 4 to 6% globally. We also see that through the case study of our extreme 2017 Portugal wildfires, this really indicates that there's a noteworthy regional influence on toxic exposure, both within the region of emissions, but also possibly more broadly through transport. And so a lot of future work is needed. So again, mentioning that we plan to do this through collaboration with the University of Aveiro collaborators. We eventually want to evaluate the impact of model resolution on implied health effects. And our goal specifically is to conduct sensitivity tests of health impacts. So looking at different model configurations by using different biomass burning inventories, different model parameterizations, just to see what sensitivities our models have to those. Yeah, and with that, thank you. I'd be happy to take questions.
Thank you. We have a few minutes for questions. Got one up here.
Thank you for the nice presentation. I'm Isabel Trigo from IPMA. So I have two main questions. One, I did not get very well how you get the mercury and PAH emissions from fires. So that was kind of blurred for me. We've been working on fire emissions for some time, and well, but the species that we look at are carbon, CO, CO2, methane. You know, I wonder if the emissions that you are looking at are very closely, and I mean closely means linearly related to these other emissions. So that was one of the questions. The other is when you look at the impacts on health impacts. Well, you showed that the hot spot in Portugal, in central Portugal, that coincides roughly with the areas where we have most of the wildfires, but it also coincides with the areas where we have most of the industries. So how will you disentangle the impacts of, you know, hard industries and from those that are the impacts of wildfires?
Yeah, those are great questions. So to address your first question on emissions, so we basically use currently the GFED emissions for getting at the burned area. For PAHs, we use emissions factors gathered from both laboratory and field studies, and so it's basically kind of multiplying that burned area by your emission factor to get your emissions. For mercury, it's actually kind of addresses your question more pointedly. It's a scaling factor with CO. And so in that case, I think mercury has been shown to likely linearly correlate with CO emissions. For PAHs, I think it's a much more complicated story. There's been thoughts that possibly it linearly correlates with black carbon, but I don't think that we have enough evidence to really know that for sure yet. And then to your second question, how we're disentangling anthropogenic and wildfire emissions. So that's really what we're able to do with our models. And so by running those three different scenarios of like the standard scenario and then turning off wildfire emissions, by looking at the difference between those, we're able to capture just exclusively the effects of wildfires while kind of subtracting out the anthropogenic effects.
Okay, any other? I actually had a slight question too. When on your model, you showed that with the correlation data, the model underpredicts the impact. So when you talked about the impact, did you correct back, or are you just presenting the model data?
Yeah, so currently we're just presenting the model data, and I think you can do some sort of like, I guess, error correction.
Yeah.
I think more interestedly, likely that is due to our model resolution, and so I think we're more going to go the route of changing our model resolution, seeing how that affects our results.
Cool.
Yeah.
Thank you. All right. Well, thank you. That was great. By the way, you'll notice the student did the best job responding to the questions. All right. So we're going to take a break now, and I think we reconvene for coffee at 11:30. So thank you.